Hello. All right, thanks, John, for introducing me so that I can introduce Dick here. Dick McCray received his PhD in theoretical physics from UCLA in 1967. He went on to have numerous positions at Caltech, the Harvard College Observatory, and JILA, the Joint Institute of Laboratory Astrophysics at UC Boulder. He stayed there to later on become the George Gamow Distinguished Professor of Astrophysics. He has also held visiting positions at the NASA Goddard Space Flight Center, Beijing University, Nanjing University, the Space Telescope Science Institute, and Columbia University. He retired in 2004, becoming Professor Emeritus, now lives in Berkeley, where he is a visiting scholar at the Berkeley Astronomy Department. Professor McCay's research is in the theory and observations of the dynamics of interstellar gas and cosmic X-ray sources, supernovae and supernova remnants. For over the past 30 years, he has been deeply engaged in the study of the evolution of supernova 1987A through both theoretical modeling and observations with major observatories such as the Hubble Space Telescope, the Chandra X-ray Observatory, VTL, the very large telescope, and most recently ALMA, the Atacama Large Millimeter Array, which he'll be talking about right now. So please welcome Dick McCray.
Well, you can see on the screen that that's not 1987A. I think it's my most cited publication. And I wanted to give a little reminiscence of my time with John at JILA. I think John arrived at JILA within a year of the time I arrived at JILA. And at the time, JILA was really the center of stellar physics because John was leading the theoretical interpretation, the famous Castor-Abbott-Klein theory for strong stellar winds. And Peter Conti had a great observational program for observing the winds of O stars and Wolf-Rayet stars. And I was brought to JILA to think about interstellar gas. And at the time, the Copernicus satellite was very good at observing ultraviolet absorption lines from interstellar matter. So here was all this activity about stellar winds, and I was thinking about interstellar gas. And then I said, well, what do these winds do to the interstellar gas? Well, they create cavities. And so with a graduate student, Bob Weaver, we wrote down some equations for the evolution of these shells. And by this time, I'd gotten used to John. My modus operandi with John is anytime I was stuck on mathematics or physics, I'd trot it down to John's office and I'd get a clear explanation. So we had these equations, and so just by habit, I took Bob Weaver down to John's office and said, we got these equations we got to solve for stellar winds. And John looked at it, and within less than a minute, he said, yeah, that has an analytic solution. Wow. Okay. And then after that, we realized that at the outer layer of this bubble, that there has to be, it's not just a sharp hydrodynamic discontinuity, but there has to be a transition region where it goes from the interior of the bubble temperature, which is maybe 1 million degrees, down to less than 10,000 degrees. And the structure of that interface was dominated by electron conduction. And so we were able to write down a little equation for what would be the column density, what would be the thickness of this in, say, the oxygen 6 resonance line, 1035 angstroms, because that's what the Copernicus satellite was observing. So we posed that question, we wrote down an equation. I went to my office, and within hours, we achieved an identical result. And furthermore, that column density of oxygen 6 was just about as observed by the Copernicus satellite in front of all these O stars. And then at the time, the title of that paper, the working title was something like Circumstellar Shells Created by Strong Stellar Winds, or something like that. And we had a visitor, a woman astronomer named Beatrice Tinsley. We showed her the preprint, and she said, oh, it's something about those bubbles of yours. That's the first time we had the bubbles. And that was an inspired choice, because I'm sure that if we'd gone with the first title, the citation rate would have dropped by a factor 2. Of course, it was a misnomer, because bubbles are not, the physics of bubbles is dominated by surface tension. And these rings around stars, there was no surface tension to bother with. Well, anyway, that theory of interstellar bubbles was quite close to the theory of supernova remnants. And then we went on to think about multiple bubbles, or multiple supernovae, which expand and grow just the way interstellar bubbles do, but they get bigger because of more energy. And then supernova 1987A went off, and I was distracted. So I've been working on it for 30 years. The theory of interstellar bubbles and all of its ramification has legs of its own, and it's still being developed. But I'm going to talk about 87A because I haven't kept up with that theory the way I should, and I certainly have kept up with 87A the best I can. So there it is, this beautiful ring with that ring was totally unexpected. It's about a light year in radius, and here's the central object. That's the supernova, and this, as you'll see in a minute, is caused by a crash of the outer debris of the supernova with a pre-existing ring. That ring was there as circumstellar matter. The ring was actually made by the star that turned in the supernova and was just expelled into interstellar space by mechanisms that we don't really understand. It's not a sphere, that ring is a tilted circle, tilted at 45 degrees, which accounts for the ellipticity. And notice the central object is very amorphous, dark in the center, and very faint. This picture was taken in about 2005. It hasn't changed much since then. Okay, I'm going to talk about I hope I can have time to talk about three topics. And one is dust formation, and the second is mapping the impact of the supernova debris with this ring and the circumstellar matter, and the third is mapping the structure of the internal debris. Now, what is this about dust? Well, at about a year and a half after the supernova went off, it suddenly went dark, and the optical light dropped by order of magnitude, almost. And at the same time the optical light dropped, a far infrared continuum showed up. And that was clearly radiation by dust. Here's some light curves of the various kinds of light. Within days after the supernova, within months, the light, well here, I guess it's 200 days, the light obeyed a perfect exponential decay that had the mean life of cobalt-56 decay. Until this time, the optical light tracked the bolometric light. But then this far infrared light came up just at the same time the optical light took a dive. The ring showed up a few months after the supernova, got brighter for about a year, and then faded. That's the ring that you saw in that picture, and that brightening of the ring was caused by well, within a day after the supernova, when the shock reached the surface of the supernova progenitor star, there was a flash of soft X-rays and ultraviolet radiation. Those soft X-rays illuminated that ring and set it to glow. Do I need to say more? Let's see. Well, I'll come back to it. So here's the spectral energy distribution of the whole system today. And what you see is that in the infrared, there are two peaks. One peak is about 20 microns is the peak. And this is 170 degree Kelvin. If you fit silicate at 170 degree Kelvin, you get this kind of a curve. This green comes from the ring. But from the center, we see a lot of radiation coming out at 18 Kelvin. And furthermore, from the ring, you also see non-thermal radiation from relativistic electrons. It's a characteristic power law. Here are two images of the 87A. The one I just showed you with the amorphous center. You can see now that at this time the ring is much brighter than the supernova. But if you look at it in far infrared, this thing is now concentrated at the center. There's no gap at the center. This is radiation at 200 microns by dust. This blue, these spots are optical radiation, and this violet color is near infrared. The violet color is coming from, whoops, went the wrong way. Right there. Boy, did I. Sorry about that. Oh, I see what I've done wrong. Well, help me out.
Sure.
The blue and the orange at the center of that image is dust in the supernova debris. This green is the ring of near-infrared emission from dust at the ring and outside. Now if I go to the next one, this violet is X-ray plus near-infrared radiation from million-degree gas that's been shocked by the supernova. These little spots are optical radiation. Now I think I have a movie. Yeah. Let's see if this works. This shows the evolution from 1995 to 2005. Before I start the movie, notice that this is optical. It's observed with Hubble. The center object is brighter than the ring. And this is a star, has nothing to do with the ring. This is the glowing ring that was flash ionized at the time of shortly after the supernova. The light from the supernova during the first day had a lot of ionizing radiation. That ionized this ring and set it to glow. And then this ring just started to fade. Then something wonderful happened. So, now if I can just find this. Oh, I got it. Okay, here goes. Now you see that the central object is fading, and now some spots appear here. Spot 1, spot 2, 3, 4. And this has become amorphous now, and it's completely encircled. This is much fainter than the ring. This is a crash. What's happening is the outer debris of the supernova is slamming into that ring, and that impact is making the light of the ring now. So the ring was originally illuminated by photoionization from the supernova, but now it's illuminated by a shock. And here is you can see time-lapse sequence here, the optical, which I just showed you, the X-ray, 2 kilovolt with Chandra, and the radio emission, which I won't talk about today. And here is the light curve again, but now extending out to 30 years, more or less to today. And here's this visible light that took a dive. This is a central object. And it took a dive at the same time as that infrared radiation came up. The infrared radiation from the crash is now dominating the light. So now we can say that it's really a supernova remnant. The light is not coming from the radioactivity of the center, it's coming from the crash. What are those spots? Why is the optical radiation concentrated in little spots? To this date, we don't know, but a pretty good guess is that it's the same mechanism, the same unknown mechanism that is seen around planetary nebulae, which are known to be very hot stars shrinking down to a white dwarf, and they have winds. So this is the famous Helix Nebula, and if you look at this at higher resolution with the Space Telescope, this stuff here is these tadpoles. Now when the blast wave comes here and hits those tadpoles, they light up. That's what the spots are. So we know here that you can see these tadpoles have tails on them pointing to the central star, which is up here. And so we can see that these spots are sculpted by the action of the stellar wind of that central star. The spectrum of the supernova has, just take the right around H alpha, has a very complex spectrum. That's at the very center of H alpha, there's some very narrow lines, have a width of about 10 kilometers a second. Then there's wider lines which have a width of maybe 100 or 200 kilometers a second. And then there's some very broad lines that have width of about 4,000 kilometers per second. The narrow inner lines are from this red stuff, which is the unshocked, but part of the ring that has been illuminated by the first flash of the supernovae. The 100 kilometer a second, this pedestal is here, is coming from the shocked hotspots. And as the supernova blast is overtaking these hot spots. The very wide, broad lines are coming from the unshocked debris as it crosses the reverse shock. And we have a powerful way to analyze these observations because the supernova obeys a Hubble's law to very high accuracy. It's just an explosion. Yeah, got 5 minutes left. Well, so if you're looking at a spectral line and you're looking at this wavelength, you're looking at a slice of the explosion that is just a plain parallel cut through the supernova debris. Here's a toy model. Here's the bubble up here. There's a reverse shock here. This is the reverse shock, where this is the freely expanding supernova debris. And this is what the supernova blast is going to hit. It's going to hit this, and here's the dense ring right here. So we made a toy of a dense gas, and this blast wave here hits this, enters into this, and sends a reflected shock back. You know, I'm going to, given the shortness of time, I'm going to skip this. It's fascinating. We really want to know what the interior of the supernova is like. But that has that little blob is maybe in its whole diameter about half an arc second or less, maybe a third of an arc second in the diameter of that central object. And that's where the newly formed radioactive elements are, such as newly formed nickel. And these are just two different models, hydro models, heavy-duty 3D hydro calculations. And the difference of the model is that this has a 20 solar mass envelope, and this has a 15 solar mass envelope. You can see the morphology is very, very different. You can also see that this explosion is very, very full of instabilities. Also, here's a recent gamma ray spectrometer measurement of the gamma rays, which are now dominated by titanium-44, and they're redshifted by about 300 kilometers per second. So the gamma ray is not at the center, the newly formed, but this thing is very asymmetric. Now, we'd really like to know whether there's any truth in these theoretical calculations. But the problem is that with the Hubble Space Telescope, this is the resolution of the Hubble Space Telescope, and we want to see 10 times better. Moreover, Hubble's no good for two reasons. One is it doesn't have the angular resolution, and the second is that there's no the optical light from this thing at the center. What we want to see at the center is totally obscured by that dust. But the good news is that we now have a new toy, the Atacama Large Millimeter Array, ALMA, which has angular resolution about 10 times better than the Hubble telescope. And it's looking at a wavelength where there's no dust opacity. The infrared light from that dust freely escapes the center of the supernova. And so when we turned the ALMA on here first at low resolution, we saw something really wonderful. Millimeter lines here from carbon monoxide, the 1,0 transition, silicon monoxide, I don't know, the 5,4 transition. And so we see several lines of carbon monoxide, of silicon monoxide, and they're bright, really bright. So just taking inferences from the ratio of these lines, of the total, we can figure out how much carbon monoxide is there, 1/100th of a solar mass, and it's at a 30-degree temperature. The silicon monoxide is 2 orders of magnitude less in mass and warmer. Now, with ALMA, as I said, if you look at one of these lines, like here, at this point, you're looking at the redshifted side of the line, so you're looking at the far hemisphere of the object. And so if you look at images of this, well, the ALMA receivers have 1024 channels. And so each channel gives a picture of the supernova at a given depth. So with one observation, we get a three-dimensional picture of this in the lines of carbon monoxide and silicon monoxide. And here it is. The ring is the blue thing. This is the optical observation of the hot spots. But this is the thing that we can finally resolve and see with the ALMA telescope. So I think, if I'm lucky, I can show you the three-dimensional structure here. The silicon monoxide is the purple on the inside. The carbon monoxide is rendered green. Now we've estimated global masses and temperatures, but we have the data to do it locally and see the density and temperature everywhere. And then we can put these theoretical calculations to the test. So here are some of the people that I've worked with, and everything I've done with this uses skills that I've learned from John. Thank you.
Hello. Well, thank you very much. That was a really fascinating talk. Are there any questions? Looks like we have some down here.
Yeah, your last slide mentioned the compact.
Oh, yeah. Ever since the supernova was seen, and it was first seen before any other way by a flash of neutrinos that lasted for about 10 seconds, and that signaled the formation of a neutron star. And since then, every astronomer with a new toy has looked hard for a compact object and has seen nothing. So whatever it is, it's faint. And in fact, it's so faint that we can put an upper limit to its luminosity to be only about 30 times the luminosity of the sun. Moreover, and if you compare that to the central object in the Crab Nebula, which is 10 to the 5 times solar luminosity, so this is more than 3 orders of magnitude fainter than the Crab pulsar. So this is a mystery, and I don't know if it's going to be solved. One hopes that when the James Webb Space Telescope is launched next year, it'll get a deeper look. But whether or not it'll be able to see through that dust, I'm not too optimistic.
All right, we're running a little late, but one more question. Okay, perfect. Please thank our speakers. It's really interesting. Thanks.
All right.
Okay.
Gotcha.
Where's the laser pointer? Our next speaker is Bruce Remington. Bruce received his PhD in physics at Michigan State University in 1986. He joined Livermore as a postdoc in the nuclear physics division, then E division, where he worked in the area of heavy ion physics. Later, he joined the LASER program, now NIF, where he has been since both as a project leader and a group leader. He is a fellow of the American Physical Society and has been the recipient of the APS Excellence in Plasma Physics Award, the Edward Teller Medal, and was most recently recognized here at Livermore as a distinguished member of the technical staff. Dr. Remington has performed seminal experiments in inertial confinement fusion, led the creation and development of HEDLA, the High Energy Density Laboratory Astrophysics Project, through scientific achievements and the mobilization of an international community. And he has pioneered the use of lasers to achieve extreme pressure and strain rate conditions in solid materials, also known as material dynamics, extreme pressure and strain rate. Please welcome our speaker.